Hello everyone. I once again welcome you all to MSP lecture series on interpretive spectroscopy. In my last lecture, I was telling you about relationship between the stretching force constant of a bond with respect to its stretching frequency. And as I mentioned, there are three simple equations to find out unknown entities such as stretching frequency or stretching force constant. The simplest one being nu bar equals 130.3 into square root of F by mu. Here F is in newtons per meter and then mu is in atomic mass unit. If you want to use the standard equation derived from Hooke's law, that is nu bar equals 1 over 2 pi c into square root of F by mu, here mu has to be multiplied by 1.67377 into 10 raised to minus 27 to convert AMU into kg, and rest is all right. You can calculate and find out. So in another equation, nu bar equals 4.12 into square root of F over mu. So in this, we have to convert stretching force constant from newtons per meter to dynes per centimeter. So if it is 1 digit or 2 digit, you multiply it by 10 raised to 5. And if it is 4 digit multiplied by 10 raised to 3, you are automatically converting that into dynes per centimeter. And then if you calculate at the end, there will be little bit difference will be there, but all the three equations are equally good. The simplest one being nu bar equals 130.3 into square root of F by mu. Very easy to remember, and you can practice with the table I gave where I listed reduced mass also. There is no need to worry about that one. And also I gave you force constant for all the bonds. I showed you different bonds in newtons per meter, and also corresponding stretching frequency in centimeter minus 1 in wave number was also given. So you verify and make yourself comfortable in calculating those parameters. Let me continue discussing about now the important one as far as coordination compounds and organometallic compounds are concerned. It is carbonyl complexes, and infrared spectra of carbonyl complex is very, very important to know the donor and acceptor properties of other ligands present along with carbon monoxide in mixed ligand complexes. The structure determination, number of bands in the CV stretching region, all those things are very important. If the number is consistent with that provided by the selection rule of a particular point group, may be assigned to the molecule. Again, if you look into the point group and character table, you can identify infrared active bands, and also how many bands are expected for a particular point group also you can know, that I would be showing you later. And then what is important is the stretching frequency in the region of 2000 centimeter minus 1 is very, very important for compounds containing carbonyl groups. What are the limitations of predicting the structure from the number of CO stretching modes? For example, the number of stretching frequencies what we observed in the spectrum may not really tell the fact that how many CO groups are present. So that means we should try to see some relationship between the molecular structure of a compound and activity of the CO stretching modes for a given point group or for a given geometry. For substituted carbonyl complexes, when we consider substituted with non-homoleptic carbonyl complexes, in that case point group may be assigned considering the local symmetry of the metal and the carbonyl groups provided the ligands have the spherical symmetry. It is very important. You can assign point group considering the local symmetry of the metal and the carbonyl groups provided the ligands have the spherical symmetry. If not, considering the symmetry of the molecule as a whole. So either way, we can correlate the geometry with respect to number of carbonyl groups present and also number of stretching frequencies are observed. For example, you consider here cyclopentatricarbonyl manganese, and also another example is tetracarbonyl vanadium with CP group, cyclopentadienyl vanadium tetracarbonyl, or you have here tricarbonyl benzene compound of chromium or molybdenum. And if you try to do the electron count also, you can do it here. Manganese in +1 state. If it is manganese in +1 state, we have 6 electrons are there and 6 electrons are there and 6 electrons are there. This is an 8 electron complex. This is another method to make yourself about electron counting, and here again 6 are there and then here 4 and +8 because vanadium is in +1 state. So this is also a 8 electron complex, and here it is 6 plus 6 plus 6. This is also 8 electron complex. So all are 8 electron complex. So we also learned about counting the electrons. This is by you can use ionic method or covalent method, doesn't matter. So all these compounds show 2 stretching frequencies when you look into the AR spectra. If you look into the first one, it has C3V symmetry, and the second one has C4V symmetry, and third one has C3V symmetry again. So that means both cyclopentadienyl group and also eta 6 arene are axially symmetrical with respect to these point groups. Symmetry is lowered if aniline or thiophene replaces arene, benzene or cyclopentanyl group, then the symmetry of the whole molecule has to be considered. For example, if you see here, you can see the symmetry is here in case of tricarbonyl cyclopentadienyl manganese, and you have a C3V is there. You can also have C3V, and here you can have C4 axis of rotation. So that means basically you can consider the symmetry of the molecule as a whole because the other ligand is also symmetrical with respect to the point group that is identified. And then if you consider here, if you put a heteroatom to make it thiophene or adding nitrogen to make it pyridine, then what happens? The symmetry of the molecule is lost, and then the symmetry of whole molecule has to be considered here. As a result, what happens? You will see 3 in case of this one as well as 3 in case of this one stretching frequencies. So 3 COs will be observed in both the cases. The trends in stretching frequency of compounds belonging to a series having related structures can be interpreted using simple bonding scheme. For example, how to make these compounds? For example, we take homoleptic carbonyl, for example, iron pentacarbonyl, or chromium molybdenum tungsten hexacarbonyl, or manganese Mn2CO10 or CO2CO8 in case of cobalt. If we shine UV light or thermally also we can activate in presence of ligands to have a series of compounds of this formula. Then after making these compounds, just if you subject them to infrared spectroscopy, that will give you some idea about the number of stretching frequencies present and also probably local symmetry. And then this is the MO diagram for carbon monoxide, and I'm sure you're all familiar with carbon monoxide. And if you consider simple Lewis dot structure, so here we have 4 and here we have 6, 10 valence electrons are there here. And then initially what we can do is we can put a bond here, and then one bond is there, and then put something like this, and then the remaining 2 electrons will be put like this. So now Lewis dot structure, okay, octet is not satisfied for this one, so these electrons will come here and these electrons would come here. As a result, what happens? Triple bond is established, and this lone pair remains and this lone pair is there, and you know that this lone pair on carbon is responsible for carbon monoxide to act as a neutral ligand, and this lone pair is what shown here. And then these 3 sets of are shown here, these 3 represents, and then this one is shown here. This is deeply buried. As a result, what happens when CO is acting as a ligand, it can never use this lone pair for coordination, it only uses this. And many times students often get confused that when it's bridging 2 metal centers, it acts as a 4 electron donor, very similar to halides. That is not true. When it is bridging with the 2 metal centers or 3 metal centers, what we are doing is we are generating electron deficient compounds. So here if you make it, it is a 4 center 2 electron bond, 4 center 2 electron bond, and if you have something like this, it is 3 center 2 electron bond. See, whatever the electrons are present here, this will be shared between 2 metals. So these things I would tell you what would happen when it is acting as a terminal ligand, bridging ligand, tri-bridging ligand, what would happen to stretching frequency we can consider. So this is what we should focus on. And then what happens, we have the pi star is also there. The pi star energy of CO is quite comparable to T2G orbitals or dxz, dyz and dxy orbitals of metal complexes, which essentially are non-bonding in the absence of back bonding or pi bonding. So they interact with pi star to generate a set of bonding and anti-bonding orbitals, and these bonding orbitals would be taking electrons from metal that we call it as back bonding. And one also should remember the fact that one carbon monoxide can take anywhere between 0.2 to 1.6 electrons to its pi star orbital through back bonding. This is d pi, I would say pi star bonding, or I would also say it's a d pi means here it is a dxy, dxz or dyz. Okay, now you can see again. So this represents sigma bond formation. 2 electrons are there, and this is CO bond formation is there. This is sigma, and then this interaction, it can be with any of those orbitals such as dxy or dxz or dyz. So this pi star would interact, and this is called pi bonding. This is pi bonding, and this is sigma bonding. So when sigma bonding would make carbon monoxide electron deficient, as a result what happens, pi bonding will be initiated, and when the pi bonding is there, carbon monoxide is electron rich and sigma bonding will be more strengthened. So this is called synergistic effect. Because of this one, what happens, metal to carbon bond is stabilized. When more and more metal to carbon bond is stabilized, CO bond will be weakened and it will be elongated, and the stretching force constant decreases, and also CO stretching frequency also decreases. So these two modes of bonding are mutually reinforcing and is called synergic effect. Charge removal through pi bonding leads to more extensive sigma bonding, while charge donated through sigma bonding thus facilitates further back bonding. So this mutual give and take benefits the metal to carbon bond, and it will be more strengthened and becomes more and more stable. Let us look into some reactivity here. When we consider metal hexacarbonyl such as chromium, molybdenum, tungsten hexacarbonyl, and when we react them with only nitrogen donor ligands which are sigma donor in nature, for example, acetonitrile, benzonitrile, or if you take triethylamine, only alkylamine or arylamines. In this case, what happens? Maximum replacement of only 3 carbon monoxide is observed here, because since nitrogen donor ligands are good sigma donors, to minimize inter-electron repulsion and also to stabilize the metal in its zero valence state, more and more back bonding has to be considered. So minimum of 3 carbon monoxides are needed in such cases to minimize inter-electron repulsion so that zero valent metal is stabilized. So in this context, when we are considering only sigma donor ligands, in case of hexacarbonyls, we can replace only 3 of them with these things. On the other hand, if you consider sigma donor and pi acceptor ligands such as phosphines, it's possible to replace up to 4 carbon monoxide, and if the phosphine is much stronger, like trifluorophosphine, it's very easy to knock off all carbon monoxide to form homoleptic phosphine complex. For example, if we take TrCO6 and if we use 6PF3, it is possible to get rid of all 6 carbon monoxides to get a homoleptic PF3 6 complex. Or one can also see some other compounds like bidentate ligands like this. Even this ligand is comparable to almost its pi acceptor ability to carbon monoxide. It can also, if we use 3 equivalents of them, it can also replace our carbon monoxide to form something like this. So such compounds have been well established and reported in 1980s and 1990s. So what we should remember is, as far as infrared stretching frequency is concerned, free carbon monoxide shows around 2133, or in some books say 2147. So one can consider 2140 or something. And in case of metal hexacarbonyl, the range is around 2000 centimeter minus 1. So that means there is a considerable drop in the stretching frequency. This is because of the population of electrons into the pi star of CO, decreasing the bond order. So increase in negative charge on metal is observed by new CO changes. For example, when we consider isoelectronic series such as MnCO6 plus, chromium hexacarbonyl and vanadium hexacarbonyl anion, we can see what would happen to the stretching frequencies when we go from cationic to neutral to anionic. Stretching frequency drops because this is electron rich. When it is electron rich metal, more and more electrons density goes to the pi star. As a result, metal to carbon bond is strengthened and CO bond is weakened. And whereas here it is in positive charge, as a result, it reluctantly donates electrons to the pi star of carbon monoxide. As a result, what happens? Stretching frequency would be a little higher compared to this one. So we can consider the overall equilibrium of metal to carbonyl bond with two extreme cases in this fashion. When moderate back bonding is there, something like this, and the back bonding increases, becomes almost ketonic. And here, if the back bonding is quite extensive, then we can have a situation like this. These two are the extremes, and here this is the with good donor and acceptor properties of the other ligands, it can exhibit something like this. So stretching frequencies are given here. You can see 2096 quite high, and it is 2000 and 1859. So as the electron density increases on the metal center, stretching frequency also decreases because more and more electrons will be promoted to pi star. This also we can call it as charge transfer, metal to ligand charge transfer. In spite of its isoelectronic series, because of the positive charge and negative charge, this observation can be made easily. So now I have given for D10 complexes of different metal ions here: silver, carbon monoxide plus, and NiCO4, nickel tetracarbonyl, and cobalt tetracarbonyl anion, manganese hexacarbonyl cation, neutral chromium hexacarbonyl, vanadium CO6. For just comparison, I have given here values. Free CO is 2143. You can consider this as the standard value. And then in case of Ag plus, it is 2204. It's little higher than the free gaseous. And then nickel tetracarbonyl considerably higher. So that means in nickel tetracarbonyl, it appears that the back bonding is not extensive. And of course, if we consider overall 3D, 4D and 5D metals, early metals, despite having electron deficiency, they are excellent pi donors. On the other hand, despite having large electron density among the late transition metals, that means I am talking about iron afterwards, and having more electron density, still they are reluctant pi donors. That can be seen here by simply looking into the stretching frequency of carbon monoxide that is bound to these late metal ions. Silver, it is 2204, and then nickel tetracarbonyl 2060, and cobalt tetracarbonyl anion 1890. Here it is more because metal is anionic and more electron density is there, and stretching frequency will be very less compared to other one. And then on the other hand here, manganese plus, so positive doesn't donate very easily, so it comes around 2090. Chromium hexacarbonyl, moderate 2000, and again here anionic, and stretching frequency further drops to 1860 compared to 1890 in case of cobalt. This also indicates early metals are very good pi donors. So increase in the electron density on a metal center results in more back bonding to the carbon monoxide ligands. More electron density would enter into the carbonyl pi star orbital and weaken CO bond. Therefore, it makes metal to carbon monoxide bond strength increasing and more double bond like character here, what I had shown in my previous slide. So now let's look into chromium hexacarbonyl to see how back bonding happens. So here we have 6 carbon monoxides are there, and we have taken ligand group orbitals are there. Symmetry adapted linear combination of atomic orbitals are concerned here in polyatomic molecules. And here 6 ligands, 6 carbon monoxide will be having symmetry of A1G, T1U, EG to match with metal 3D 4s and 4p orbitals. So 3D we have EG and T2G because octahedral splitting, and then of course 4s is A1G and 4p triply degenerate, T1U is there. Now they combine in this fashion to generate 6 CO bonding orbitals in which 12 electrons would be accommodated here. And then these 6 electrons, whatever is there on 0-valent chromium, will be sitting here. And then these electrons, as I mentioned, would interact with this orbital, T2G would interact with pi star, having T2G symmetry to generate bonding and anti-bonding orbitals of pi symmetry, and then these electrons would come here. So this would explain sigma donation as well as pi acceptor properties of carbon monoxide. This is for nickel tetracarbonyl. So nickel tetracarbonyl, we know that nickel is in 0-valent state and it is tetrahedral. And then valence bond theory suggests sp3 hybridization having nickel something like this, and then CO will be binding something like this. Actually, the molecule is tetrahedral in nature, but when we look into the MO diagram, valence bond theory says without any hesitation that it is sp3. But when you look into molecular orbital diagram, it gives a different hint about the geometry. And if you see Nd here, if you consider here 3D, and 4s and 4p are much higher in energy. And then if you just look into the sigma and pi bonding orbitals of carbon monoxide, 4 carbon monoxide, these are not at all interacting. These two are supposed to interact with this one and this one, A1G and T1U from 4s and 4p to establish 4 nickel to carbon monoxide bonds. But that's not seen. And here they remain as non-bonding. So here as non-bonding, and there is no interaction whatsoever with this. That means basically sp3 hybridization predicted from valence bond theory doesn't explain bonding in nickel tetracarbonyl. And then, but what you can see is here we have pi star orbitals of 4 COs. They are interacting with T2 here, not T2G, T2 I would say, to have back bonding. That means NiCO4 survives only on back bonding, but there is no sigma bonding. That means these electrons are more or less confined to carbon monoxide itself. They are not forming nickel sigma bonding at all. You can see here, all are here. I would show you in the next slide, you can clear here. Well, you may be surprised why I have shown so many electrons here. Of course, if you consider here 1 pair, 2 pair, 3 pair, and 4 pairs are there. 4 pairs per carbon monoxide, and 3 for triple bond, 1 for lone pair, and similarly we have 12 electrons. 4 pairs are there. 4 into 4, 16 pairs of electrons should be there, and this is deeply buried. This can be ignored. Those 16 pairs should be shown here. All these 16 pairs are shown here. That's the reason it looks complicated. But our attention should be towards these 4 electrons here. So they are not at all involved in binding. So you can see here. So these are supposed to interact with this as well as this one to make 4 nickel to carbon monoxide. So these ones. These are nothing but these electrons on carbon monoxide. So this is not, they remain almost like non-bonding. So that means how the carbon monoxide are held, it is because of back bonding here, E and T2 here, and it splits here into E and T2, and then these 10 electrons from D10 system are occupying here. So that indicates why NiCO4 is highly volatile, highly unstable, because it doesn't have any nickel to carbon monoxide sigma bonding, unlike chromium hexacarbonyl, where we saw there is chromium to carbonyl sigma bond in all 6 carbonyl groups. Okay, so here we have both, whereas here we have only this one. Not this one is missing because they are non-bonding here. This electrons remains non-bonding. They are not interacting. And many textbooks are not showing this one. And of course, if you want to look into more, you can look into these references that I have shown here. So now let's look into the effect of different types of ligands on new CO, that means stretching frequencies in mixed ligand complexes. So one system I have taken here is tricarbonyl molybdenum complex having different type of phosphines and other nitrogen donor ligands. And if you consider here, tris trifluorophosphine tricarbonyl molybdenum complex is there. 3 carbon monoxide groups are replaced by PF3, and as I mentioned, PF3 is an excellent pi acceptor. It's a poor sigma donor but an excellent pi acceptor. As a result, you can see stretching frequencies are much higher, very close to free CO. But when you replace PF3 trimethyl phosphate, it is relatively weak pi acceptor compared to trifluorophosphine. Here considerable drop is there in the stretching frequencies. That means more back bonding is observed. On the other hand, when you go to triphenylphosphine, triphenylphosphine is a good sigma donor but moderate pi acceptor, and it is less weak pi acceptor compared to trimethyl phosphate. Further it drops here. Then if you consider tris-carbonyl complex with astronitrile, astronitrile is only sigma donor, and now only 3 carbon monoxide are there, it further drops here because more back bonding happens to remaining 3 carbon monoxide groups. And then in case of pyridine 3 also, it is much relatively lower. This indicates how the ligands present along with carbon monoxide can influence the stretching frequency of carbon monoxide. If they are competing equally well for back bonding, their stretching frequency increases. On the other hand, if they are weak, the ligands that are incoming are weak pi acceptor, then stretching frequency drops considerably and CO bond becomes weakens. Okay, so let me stop here and continue more discussion on metal carbonyls and their stretching frequencies in my next lecture. Until then, have an excellent time. Thank you.